Hi, everyone, and welcome to another NL seminar. We're excited to have Hao Zhu from Stanford here today. Before we get started with this seminar, I want to remind everyone, number one, we still have a lunch opening for today, so someone come get a free lunch with us. And number two, we have 2 NL seminars left of the semester, next week, the 24th, and the following week, May 1st, which will be virtual. And yeah, please come out for the last 2 talks of the semester. So we're very excited to welcome Hao Zhu for his talk on ushering AI agents into an open social world. He is a postdoctoral researcher in the computer science department at Stanford University. He finished his PhD from CMU. He's interested in AI agents, human-agent interaction, robotics, and embodied AI, and what AI agents tell us about human, social, and embodied cognition. So please welcome Hao Zhu.
Thanks so much for the introduction. So I'm Hao Zhu. I'm currently a postdoc researcher at Stanford, and I'm very excited to give a talk today. So my talk will be focusing on agents and more specifically large language model agents. So I want to ask you about your definition of large language model agents. So very obviously, they are not the agents that are carry out the special missions that we give them, like FBI agents. For a lot of public that I have interacted with who do not have the technical depth as we do, they may think like AI agents as some replacement of the human assistant that will take your call and handle some tasks that you give them, sort of like FBI agents, but not that secret task. And from the RL community, people have been studying agents for decades. They are most likely to be defined as the decision makers, which take in like observations from the environment and carry out some action upon the environment, change the state, and get observation again in this interaction loop. And the second definition that often are used for agents these days for a lot of online courses, online materials, they may think agents as the ones that are connected to the tools, external tools and services, or some memory, etc. The most recent instantiation, which is very popular these days, is called MCP, which is published by Anthropic, and basically they want the external services to provide their own servers so that they can connect the large language model with those in order to augment the capability. So who here, I cannot see the people in Zoom, but please raise your hand if you think LM agents as the decision makers. Agree with the next definition. Who here think they are models, large language models that are connected to services, tools? Mutually exclusive? Yeah, they are not mutually exclusive. And that's the point. Like, I think they represent the 2 ways of thinking about agents. One, I would call it agent thinking. It's mostly adopted by people who come with like RL background. They think they are decision makers powered by large language models, and then we can treat the agents as not too different from like the recurrent neural network agents or other LL agents, but they just are powered by LM. They can use a lot of good properties, which I will talk about in a few slides. And they can, the policy is also, introduce a good prior for the policies. And the second kind of thinking is LM thinking. So there are a lot of capabilities of LM, and we can make full use of them so that we can create the agent as in a zero shot. Basically, we can just apply all of the capabilities of LM, which are often called agentic. This is very popular buzzword these days, and it's very weird. It's still got out-of-practice by this. Cool. So there are a lot of emergent capabilities of LM. In the previous in the lab meeting, also we discussed a lot of like the induction or this kind of capability, long context learning capability LLMs, and they are what most likely they are not the emergent that people think them are. But most likely they are trained on specific data, or their architecture actually enable this capability. Like they are trained on like have repo memory because they are trained with long context text or news or other articles. In context learning, maybe it's because of specific like a data pattern. Forming is also because they are trained on a lot of like tags that have a lot of connections with the physical world. And if we think from the agent's perspective, there are specific capabilities that we are looking for in an agent. First is a perception. Basically, the capability of looking at the current state and also looking at the past history of the interaction. Planning is the other side. It's looking into the future. What's in the possible futures that we should choose? What are the strategies that we should choose to make sure the probability of reaching our target is maximized? Agency is weird. There are a lot of definitions of agencies. The agency definition I would adopt is the capability of recognizing itself as an individual. It has its goal and it can have the motivation to pursue the goal. And lastly, it's about learning. So the agents can adapt to the changes of the environment. Also, it can accumulate the experience through the interaction and use those experience to improve its own capability. That's the learning. So if we connect these emerging capabilities with the agentic capabilities that we are looking for in agents, we can see a lot of connection with them. I will not go into too deep about how these are connected, but we can see, for example, in-context learning could be useful for learning. Very obviously, can use the positive experience as an example, and in the future, I can use it. And so coding is very useful for planning because when we are writing code, we often have like good abstraction of the steps and implement the detailed steps, detailed implementation of the functions in other files, in other functions. So it's also very useful for planning. So basically, these emergent capabilities of large language models becomes very useful in creating agents. And that's the reason why the current, even if you just use as an agent in a zero-shot manner, you don't tune the parameter. You just feed the current observation, the goal to the model. We can get a reasonable, for a lot of the tasks, we can get a reasonable performance. So in this talk, I want to give another view of this. That is, most of the agents work these days are developed. By developed, I mean evaluated, trained in sandboxes in a very confined space. Even in the previous era, pre-ARM era, ARM agents are typically trained in this way because we can get very high number of frames interactions with a limited time. So following that trend, researchers have been creating this environment also in this confined space to ensure that the evaluation are rigorous. We can replicate everything, but basically confine them in the sandboxes. I give the two of the previous work that I am part of. WebArena is a web browsing environment where we have self-hosted. All of these websites are self-hosted. They are realistic, very similar to the real-world website, but they're completely self-hosted. So we have the full control of the databases. So we can have very rigorous evaluation of whether an agent can complete it or not. This Sotopia is a multi-agent environment where we instantiate the personality of each of the agents through automatic generation, but we fix all of the persona in there and simulate the interaction between them. We also ask a human to control the agent, how they operate the agent, but the human are not really the human in there. They are not representing themselves. They are still be seen as the a persona in the environment. We just want to test the human and the agent's performance gap. In both of these worlds, and there are a lot of papers that are also following this trend, like OS world, which not only looking at the website, but also look at the full operating system. And there are agent company that is also follow up that will consider maybe the merge of these two, so they both have a task completion auto interacting with simulated colleagues. But the problem of the sandbox environment, I would say, is that first, all of the data that we collected from this environment are task-driven. Basically, we give the task and they have the interaction. We could have successful and the failure experiences, but all of these data are still task-driven. And second, because there's no involvement in real human, the model's performance evaluation training are not aligned to the human. And lastly, because we don't have the alignment with humans, with some models that may not have the same policy as the large language model agents, there are coordination failures. So I will show you a few papers these days have been studying these failures. First one is called CoGym. It's studying human AI collaboration, and the top two failure mode of the agents are communication and situational awareness. And the second, there's a paper called Why Do Multi-Agent LM System Fail? And the top failure mode are disobey the task and rules specification, coordination, loss of conversation history. And similarly, in the HRI field, human-robot interaction field, they're not really studying LM agent, but still they can find the reinforcement learning trend in the robot. They may not be able to follow the social norms. For example, here, they give the example is that when the robots interact with humans, the robots look away, while human might want the robot to have like a consistent gaze to ensure that they understand what the human says.
Question?
Yeah.
Oh, maybe again.
Yeah, go ahead. Yeah.
When you're adapting the LM into an agent using a sandbox, like what's the kind of training that's being done? Is it like, what are the labels? Are you like seeing if you use the right tool? Are you judging based on task success? And kind of, maybe that's related to that slide about what the limitations are, but I'm just curious.
Yeah. So most of the work, the first round of the LM agents are zero shot. So there's no adaptation, there's no training in there. And then there's another round of method. Even right now, there are new methods being proposed to collect this experience. So for example, when you interact with the environment, when you use the tool wrong, then you likely get some failure messages from the environment. Then you can label those as the wrong ways to use the tools. And in the future, you can learn from that. You can provide it in the context. Same thing also works even better. It works even better if you use the positive experience. So if you try different ways of using tools, you will collect a lot of cases where you call the tool, you get the answer that you want, and you can collect it in your history. So that is another run. And there's also the parameterized training. If the previous one is non-parameterized, there are parameterized training as well. Yes, I will also introduce that later. Yeah, so how to solve this kind of failure mode, I would think about this as an optimization problem or a search problem. So basically, if you think about search problem, you should have a search space, basically the constraints of all of the solutions, and you should have the objective, and also you have the optimization algorithm. So if you want to solve these ones, you might want the objective to be human-aligned evaluation. You might want the constraint to be some form of the social norms that we might expect the models or other humans to perform. And lastly, you want to optimize that. And for humans, often it's a social intelligence if you want to complete your goal within the given social norm. So the idea and the topic of this talk is we transform from the sandbox to an open social world. So what are in this open social world? We have the world like the open-ended, open world that the model can interact with. This could be physical world, which is open, and it can also be digital. It can also be like the online world, like the websites that are not in our confined space. And also it includes the humans. It should directly interact with humans, get humans feedback, get humans interaction, and learn from those interactions. And lastly, if like the interaction with a human is too costly for training, you can also have other agents in the interactions as well. So I would say this is apply a certain kind of thinking tools into the human thinking. We think from our perspective, how humans are learning social intelligence, how humans are solving the optimization problem is through the interaction with this world. We don't live in just live in a playground and play with our computer. We interact with real humans, and we learn to interact through interaction. So the first part, I will talk about how to a special way of interacting with a human, that is inducing the metrics from the open-ended feedback. So if you consider a web agent or like computer use agent is also similar, you might give it like an observation, like something like this. For example, this is an e-commerce admin portal. And the task could be something like, please find the latest order which is on hold. The desired behavior is that they use this UI element, maybe first click the status, click on hold, sort by, and time. Do this sequentially, one by one, and then it should be able to find the correct answer, pop up in the first line of the form. And an undesirable trajectory will be the agent directly copy paste the task into the search bar, which may not be supported. At least in our self-hosted website, it was not supported, so you cannot get the one that you get, the desired output. So to evaluate this agent's performance is very related to what you just said. Most of the methods are goal-oriented. That is, just check whether the agent has completed the goal or not. And then the other side of the other kind of evaluation is the behavior evaluation. That is also evaluating the manner that the agents complete the task. So I'll give you a different example. Let's say the task is to close the door. Goal-oriented evaluation checks whether the door is closed or how much of the door is closed. Behavior evaluation differentiate slamming the door and closing the door gently. These are human aligned in some way because it's not very easy to differentiate between these two. Maybe you can judge by the sound produced by the door or the speed, but it's very hard for you to have like a threshold of how to tell like slamming the door from closing the door. And it's very domain specific. Even for this one single case, it's hard to have evaluation function. How can you generalize to a lot of like cases. So as a result, most of the behavior evaluation are ungrounded. Even the one that I proposed in my previous papers they're ungrounded in some way. I will show you some example later. But manually designed the behavior evaluation are often too high level to be comprehended by LMS judge, and it's not easy to design a rule-based evaluator to evaluate this behavior. So give you two further examples. First one, in web arena task, let's say the task is the post 3 question mark in the Reddit thread, and the agent could post that 3 times. So from pragmatic perspective, this is not correct, because when humans say this, they don't want you to post it multiple times. But the evaluator we have in web arena just to check whether this message is in the database, and it is in the database, so they get a +1 reward. First, let's say in the Zootopia, the task is that we ask Alice to ask Bob to lower their voice in the library. And Bob will address it. I will lower my voice, but do you want to discuss our weekend trip? So apparently Bob knows that, acknowledge this suggestion, but also doesn't really know that what they mean, otherwise will not continue the conversation. But the LMS judge may still think that Bob is doing a good job. It follows social norm, because it's a social norm is not completely defined what is really lower the voice in the library. So how do AutoLibra resolve this? First, we propose a method that can do data-driven metric discovery from the human feedback. And second, we use a very strong capability from the large language model, that is the capability of understanding the semantics and matching the similar semantic together. We use LM to do semantic analysis. This might be foreign for people who are not in the HCI field, but this is a common use in HCI. That if you have a lot of opinions, a lot of feedback, you can first code them and then group them together. This is often called semantic analysis, often done by humans, but I found that it is also used. It's a pretty easy job for to do. And lastly, after we extract this metric, we make it a closed loop optimization process. That is, we evaluated the metrics and the LMS judge together to see whether they can really recover the human feedback. So we can have a bunch of human feedback and we induce the metrics. But we want the true evaluation of this is whether the metrics are useful even for unseen human feedback. So this kind of a closed loop optimization makes sure that if it can recover the human feedback, at least the two things should be right at the same time. First, the metric should be good, and the second, the LMS judge should make the correct decision. And just give you a preview of how well this is working. We use it first as a lens. Basically, the tool we use for understanding agent's behavior. One very ungrounded, very high level metric in Zootopia is called believability. Basically, how believable the agent is as a human. But we found that with AutoLibra, we can extract much more grounded ones, like conversation naturalness or personality consistency, etc. For Web Voyager, the authors did a post hoc analysis of the agent's behavior, and they found the #1 problem is the navigation stuff. But there could be a lot of different ways to the navigation stuff, and our method could recover different navigation stuff reasons. And we can also use this as a ladder, basically as an optimization tools for agent. And here we use 2 different ways to optimize the agent. One is more human involved. We as a human to do prompt engineering for the agents. This actually, although for people in the academia, we think this is very silly, very stupid way of optimizing LLM. But in the industry, there like prompt engineering is a still very useful way. So we found that with the AutoLibra, we can give a reasonable understanding of the agent's behavior. We identify the problems of the agent, and that will guide us to update the prompt. And also after we update the prompt, we can use the extracted metric to see whether our desired aspects are improved significantly. And after the agent's performance is improved, we can induce more metrics because they encounter more problems that were not made previously. And this can be done iteratively. And in the end, we can extract a lot of different metrics, and in the end, we can reach the success rate a lot. So this is on the game I will show later. It's called the Bubbles AI. It's a very challenging game, even for humans. And the success rate went from 33 to 55%. And for web navigation, we did a different way. We have automatic improvement, that is fine-tuning the agent's parameter, but on selected data. So we use this metric to select the data for fine-tuning the agent, and we show that this can also be done iteratively, and we can have a continuous improvement. This is not trivial because previous people have tried multiple times to use LMS judge as the data selection method, but normally they will converge very fast. They will not get too much improvement after the second round.
Quick question.
Yeah.
Well, I guess why is there a bottleneck there? What's stopping them from?
Yeah, because the LMS judge cannot provide new because if you use a fixed evaluator, you will converge to that. Yeah, but here, because we give the human feedback in each iteration, we have new metrics coming out at each iteration, so you can get a continuous improvement.
Sorry.
So to understand you said human evaluation. Human evaluation?
Yeah.
So the idea here is the model does something, you have a human look at it and write free text about what went wrong. Yeah. And the point is, can you take advantage of that? Yeah. And it's not just on the data, on the instances that the human has labeled. Humans have labeled, but we induce the metric that it can be used for the whole data set. So if the human label like 16 in here, each round we only annotate 16 data points, but we applied it to 10,000 data points. Generalizing from 760 things to try to. Yeah.
Can you talk more about like how you induce the metric from the free text feedback, and like how you make sure that those metrics are, I guess, like grounded in what is actually a useful skill for the LLM? Yeah. So that's exactly what happens. Okay. Yeah.
Maybe you'll get into this too, but I was thinking, like, why don't you train the evaluator to rewrite the prompts, and then you have human prompts too. Human prompt edits, right, as well.
Yeah.
You could train like the evaluator to write good prompts, and then it's in a loop.
Yeah, exactly. Yeah. I think that's a really good idea that we should try later. Yeah, this is just like we just want to show that this is a good optimization target, but in the future we can change the optimization method. Yeah. So the input to AutoLibra are pairs of the agent trajectories and the human feedback. Just to use the example I used before, the search query could be latest order, which is on hold. This is undesirable because our search bar doesn't support that. And the human feedback could have two aspects. The first aspect is that the agent should not use the search bar, and the second, it should directly use the menu. So the first one actually is talking about the query that they put in the search bar is wrong. And the second is about the UI, the interact is wrong. So it's just in other cases, for example, the agent click on the disabled button 3 times in a row. This is actually similar to the second aspect in the previous one. It's using a wrong UI element. And the last one is the successful trajectory. And they also have like a positive feedback that is approaching the right search queries. So based on this human feedback could include like one or more aspects. So the first step of this is to ground this feedback, break down the input, which is trajectory plus the feedback, into smaller aspects. So each of the aspects in our method are defined as a triple. First, we have a behavior, and second, there's a feedback, and then lastly, there's a sign, is whether it's a positive aspect or negative aspect. So here, as I said, these are all aspects. These have like 2, 1, and 2 aspects. Cool. And then the second step, after you have all of these aspects, you can merge the ones that are similar together. So this one, all of the purple ones are talking about the interact with the UIs. So they are just different ways that the agents making wrong decisions when they are interacting with UIs. So they should be merged together. And there's one positive behavior that understand UI correctly, and there are negative behavior, bad behaviors in these two. So if you cluster these two, all these 3 purple ones together, you will have a metric that is interacting with UI. And similarly, you can also have another metric that is clustering the green ones, which is using correct search queries. So based on this intuition, we can have all of these aspects on the left. Green and red indicate the positive and the negative aspect, and then we can prompt the large language model to classify them, and then you can classify them into different behaviors, different metrics, and in each metric you have a list of positive and negative behaviors. And this is the two metrics. If you put in those human feedback plus trajectory into our system, these 2 metrics are the ones that could produce. And the third step, I have some problem with some animation. I cannot go back. Yeah. So the first part of this is an extraction process. So the first step is the feedback rounding. We turn the trajectory feedback pair into aspect. The second step, we cluster these aspects into metrics. And then how can we know that the metrics are really good? So there's an evaluation path. The first step is to use LLM as a judge to evaluate the trajectory that we just fed into the extraction process. So if we take the trajectory plus the metric, we can give each of the metrics 3 different kind of scores: the positive, neutral, or negative. And then we just remove all of the neutral ones. We'll have a list of positive trees that are ones that the LLM as judge labeled as positive, and then negative trees as well. So this is the second. So this is the first step in the evaluation path, which is the judge. You give all of the metrics, and you ask the judge to provide the evaluation. I'll have to manually do this. Cool. And then the second step in the evaluation path is called meta evaluation. Basically, if you have these 3 trajectories, and then you have these metrics, you can extract these trees, and then you can see whether these trees are covering the human feedback or not. For example, if the trees here is a positive, but the human's feedback is a negative, then it is not really covering the human feedback. If it's the same thing goes if the trees is neutral, but the human really care about the UI interaction, then it's not covered. So that will give you like a lower coverage. And then there's also redundancy problem of the measure as well. So if you have some some traits that are generated from these metrics that are not mentioned by the human, then that will be counted as the redundancy. So here, if so after the 2 passes, we can optimize for the best metrics. So if we evaluated on a range of different agent tasks, CodeGym I just mentioned is a collaborative setting where the human and the AI collaborated on the same task. and the human gives the feedback. So this one is different from other data set because the feedback from the code team are from real users, prolific users who do not have the technical understanding. And in other data sets, the Zootopia I mentioned before is a stimulated role-play agent interaction data set. WebArena and Web Voyager are both web navigation data set, but WebArena is on the self-hosted website, while Web Voyager is on live website. So in all of these cases, we can see that when we are using more metrics, we'll have a higher redundancy, which is understandable. But also when we use more metrics, we'll have normally more higher coverage, but it will reach a peak at some moment. So this number could be around 6 to 10, depending on the data set. But we still had like very high absolute coverage on like a data set, even for code-driven this kind of feedback that are not.
Sorry if you said this, I missed it. What is the blue square and what is the yellow star?
I will talk about it. Yeah. So we will still get very high coverage on the code-driven this kind of data sets where you have like the feedback coming from the users instead of from expert. All the other ones are from expert who knows how agent works. Cool. And then because we have these, we can plot all of the metrics of coverage and the redundancy on this plot. We can optimize for the set of metrics that have the highest coverage with the lowest redundancy. Basically, if at some point you found the when you increase the number of metrics, you only see the redundancy going up, but the coverage is not going up. That is the time when you can stop. And then the stars. So we use we have a held of the data set, just as I mentioned before. The true evaluation for this should be on the feedback that are not used to induce these metrics. So the stars are the coverage and the redundancy of this never seen feedback. We presumably should be drawn from the same distribution, so they are not OD, they're still in domain, they're still in distribution, but we only just get like slightly worse on the held data set. I think this shows that we didn't overfit our training set too much, but it's understandable that the performance on the training set is much higher because we have the exactly same example in there. And the blue one is that so we also did an ablation that is to remove all of the examples attached with the metrics. If you still remember, for each of the metric, we'll have a list of good behavior and the bad behaviors. We also the name and the description. The blue one, the way we get to the blue performance is through removing examples which only keep the description and the title. We get much worse coverage on the blue ones, and sometimes they even have higher redundancy.
But the different circles from different hyperparameter settings?
Different circles are from different number of metrics in the metric set,
which you control by a hyperparameter set.
Yeah, hyperparameter.
So basically, just saying how many metrics are you allowed to create.
Yeah.
But this is a cyclical thing, right? So when you do this creative metrics and analyze metrics, and so you could, right? But no, you're not changing any. You're not changing the underlying LLM. You're not changing any other hyperparameters. It's just number of metrics.
We also change the different LLM in this process.
Okay, so like those dots.
Yeah. But this is our already the best LLM that we have tried.
Oh, so it's always the same LLM.
Yeah, all of these are the same LLM. Yeah.
So I had a question about different LLMs. Are you using the same LLM like for the base of the agent and the metric in extraction and the LLM as a judge evaluation, or do you use different LLMs at each step?
Yeah. So the agents are using different LLMs than the ones that we are using, but not too different. They are all from the GPT family. So a lot of these agents, like the Web Voyager, WebArena, are GPT-4. Code team is GPT-4o. Zootopia, I think, is also GPT-4. So these are the agents LMs. The elements of judge are O3 mini. The model we use to induce metric are also O3 mini. Yeah. And we have to try the different LM to find the best one. And we do find a large improvement after we switch from GPT-4o to O3 mini.
Have you tried LLMs like outside of the GPT family?
We have tried Gemini, Gemini 1.5 Pro, but the reason we didn't use it because it's just some technical issue. We have a lower rate. We have a lower token rate. So GPT-4 works, and also mini works the fastest for us. Yeah.
The matrix is the matrix will be constant in every loop.
Sorry.
For example, in one loop, we have look into UI, this kind of matrix, right?
Mm-hmm.
So this metric will remain constant each loop, or it will get changed out.
Yeah, so each of the induction loop, it will induce different set of metrics. So we will not keep them. It is so when we are optimizing this, we are not adding the metrics into existing ones. We are inducing a completely new set of metrics. But in the previous one, when we are using them for optimization, if you still remember, we use them for agent optimization. We have different terms, right? We keep the metrics in the previous terms because we want to use them as sort of like unit tests. If you're familiar with unit tests in the software engineering, it's sort of to prevent the future features to break the previous features. So in that case, we keep all of the metrics induced in the previous terms and try to add a new metric to it. But here we are showing that we can use it for evaluating the agents. We are not to improve agents term.
And also we have a matrix of induced matrix every time. So we will be giving this induced previously created matrix information to the judge. Yeah.
Not to the judge, but to the inducer. We tell it these are the metrics already exist, that they are the ones that you should copy, and you can induce more ones adding to this set of metrics.
And the human is creating other aspects of the feedbacks, right? Mm-hmm. So is there any limit of how many aspects a human creates, or what's the category of how a human creates the evaluation?
We didn't restrict the number of aspects that the human should create. Actually, when humans are creating those feedback, they are not aware of the process that we grant the feedback. But normally the empirical number is around 1 to 4. So I have seen inducing more, but the average is 1 to 4, depending on the data set. In Koji, it's closer to 1. In Zootopia, it's closer to 4.
So is it you have aspects of 1 to 4? Mm-hmm. Only little aspects. And if you are telling inducer to take 10 metrics out of the 4 feedback, so is it due to that there is a less coverage kind of concept here?
No, so we'll have a lot of these feedbacks. So it is in the whole data set. Let's say we have 100 feedback trajectory feedback pairs. For each of the feedback, we have 1 to 4. In the end, we'll have 100 to 400 the aspect to cluster. Yeah.
Is it possible to do did you do a human coding as a comparison?
Yeah, that's really a good question. So that's the part. We validated 3 different parts of the whole pipeline. I'll show that here. So we validated 3 parts of the whole pipeline: the feedback grounding, the element judge, and the meta evaluation. The only part we didn't do is the behavior clustering, because this part will involve in coding 100 to 400 feedback, 100 to 400 aspects, and it's very costly to do. So we didn't have the human benchmark for this.
Yeah, I wonder if there's a way to do that, because I mean that is qualitative coding, informatic analysis is of course a standard part of like especially social science research. Now it's not the same as web arena. But like there definitely are those data sets around. So I'm wondering if there's a way that you could I mean, this could be used to evaluate anything, right? Like the fact that this is done on Web Arena is useful only in as much as then you can see how well it affects future Web Arena behavior. But in terms of being able to cover the space and devise good non-redundant metrics, you could use any coded data set, right? Like whatever, general design feedback or like drug events, whatever, any kind of thing.
We could use
different project.
It's different project. And you know, I feel like the coding process can also is also non-deterministic. Even the human do that.
For sure. That's the thing. So you compare that one to the other.
Cool. I'll quickly go through here. So I have shown this before. We can break down the high level, the metrics that the human have proposed. But more surprising is that we can discover some metrics that have never been proposed by the previous authors, including me. That, for example, Zootopia. It turns out the responsiveness conversation termination has never been covered previously, and the coding. There are metrics like the itinerary, one of the tasks of creating the travel plan, but the detailed quality of the report and even the formatting and the presentation consistency are also what the human care about, but are not mentioned in their paper.
Do all of the induced metrics end up corresponding to something that is like intelligible to humans, or do you end up are there cases where you induce a metric that doesn't really correspond to like human intuition?
I would say when we are validating the elements of judge, humans do give very high correlation with the model's judge. So I would say, the model's understanding of those metrics could be very similar to humans. That is the only empirical evidence I can show. And I just said it can be useful for agent designers, human in the loop optimization of the models. It could after you design the agent, you can have agent trajectory, you label the data, you send those to AutoLibra, you extract the metrics, and you can improve your prompt. Because a lot of problem in the prompt engineering is that if you update the prompt, you don't really know whether it can change the agent behavior. Even if you do case study, you are only looking at a handful of trajectory. You don't know whether that's a significant, statistical significant enough. But ours can evaluate like thousands of trajectory to tell you whether your prompt really changed the agent behavior. And you can do that in the loop, get new trajectory after you have improved your design. And also can use in automatic optimization as well. Just to show you one quick example, the original GPT-4o agent cannot perform very well on this Baba AI task. In this task, the agents not only need to achieve the weak condition, but they also need to break or form new rules. So here there are two rules. One is a stop, so it cannot go from the left room to the right room through the wall. And the second rule is the ball is win, so it have to reach the ball to win the game. But the original GPT-4 agent just stuck there. After 3 iterations, we can get to a point where it first broke the what is a stop rule and go through to the second rule, form the ball is a win rule, and go to the ball.
Do these in general for the Baba's AI task? Do these do well? Do they tend to do worse on like the more self-definitional things like when you change Baba?
They don't. We don't have that in the task suite.
Kind of situation.
We don't have.
Sorry, more like wallet here.
So this instantiation, so we use a previous implementation. It's not exactly the same as a Baba is you game. So if you break Baba is you, the game stops. The game restarts. Yeah.
So it's just basically obstructions and win conditions.
Yeah. That would be very interesting if it's tested on the original.
I didn't know this test, and it's like one of my cemetery games.
Yeah. Cool. Yeah. Yeah, I don't have enough time. I should start. I should stop at 12.
At 12, yeah. We can, okay. If you want to go through like these super quick, I also do want to allow more time for questions.
Okay, cool. Yeah. And the second one is also very exciting because we have a method that can get the data from open-ended exploration of the agents. So we explore the world in an open-ended way. As mentioned before, if you go on the web, you don't have a specific task in your mind. There's not a voice telling you, oh, you should do this. But you basically explore the world. You can do a lot of random things. Yeah. So for example, if you go onto like Apple.com, you can do maybe research the Apple Watch, the Ultra 2, find the battery life, etc. And on the left is actually if you just ask an agent to explore Apple.com without telling it exact task. And this is one trajectory that we get from zero-shot exploration from a Llama 8B model, which is pretty weak actually. And then, so this gives us an intuition that is, we can ask the model to do exploration on the real website and extract the task, look at its own behavior and do some reflection on what I had just done. And this can be done iteratively. You can induce the task every step. In practice, we use a 4. So basically, it can do 4 steps in a row and look at this 4 step and try to understand what it has just done. If it makes sense, it can continue to do this. It can go to the 8th step and do this again. If it still makes sense, go another 4 steps, etc., etc. The longest we have done, the longest trajectory we have collected is 40 steps. So it can, even the random agent can go onto the 40 step, it still makes sense. So the question, the model we propose, method we propose is called the NNetNav, and the first question, how to make Llama explore. So here we propose a way to really collect the meaningful data, because if you don't give it some instantiation, some initialization, it might not produce very diverse trajectories. So here we give it like a description of the human, maybe you're a young programmer who works at Meta, lives in Menlo Park, which is a typical situation and interested in investment. You fit this into the prompt, and you ask the large language model to produce the action given the current observation and all of the previous actions. And then the input to the model is actually not a screenshot in our implementation. We use a not multi-model LM. So we use accessibility tree as the input. And at each step, it will first generate channel sound and then generate an action. After it takes several steps of the action, we feed the trajectory so far into the LM and ask it to label it, basically generate instruction that it thinks it will lead to this trajectory. And then lastly, we want to evaluate the cycle consistency, right? We go from the trajectory to the instruction, and we also want to see whether it can whether it thinks that this trajectory makes sense to enter this instruction. So we feed this instruction as well, and then it will produce a number, a score that labels whether the trajectory works for the generated goal. We can do this a lot, and in the middle, if you find that your reward score is low, then you can prune it. Basically, it can tell you this is if the reward is 0, then you can stop doing that, and then you can start over. So this pruning actually works very well. So here, all of the green areas are the trajectories that we have collected. Red areas are the ones that we didn't explore be pointed at these edges. So you can see that we are able to just get like a very efficient proportion of the data.
What is the x-axis here?
X-axis is the it's a number of the x-axis is the frequency. The frequency of the trajectory being cut at a certain exploration step.
Okay.
Cool. And on different websites, we can get a lot of different, very complex goals that have never been proposed by the humans. In WebArena, Web Voyager, both of these data sets, they ask a human to write tasks, but those tasks are most likely relatively short because humans are lazy and not creative enough. But in this way, we can collect these complex goals, these different data set based on this trajectory. Because the trajectory can go very long, these goals can be very long. Then how can we use this method to generate the supervised data for models? One very naive idea is just use the exploration trajectory, but it may not be always optimal because the exploration trajectory can contain some suboptimal local decisions. They have cycles, etc. Although it makes sense, may not be the optimal for the instructions. So the idea here is to also use the data from the current policy. And then we can have, if we have a K trajectory sample from a current policy, we can take the exploration policy with the K policy. Altogether, we have a K+1 trajectory and ask the element trajectory to choose the one that is the best. And in practice, there are about 55% of the cases where the trajectory sample from the current policy is chosen, and the other 45 that the exploration trajectory are chosen. So we altogether we collected 10,000 demonstrations from 20 websites, and because we give them a diverse set of proposals, we have a diverse like the set of intents over 100 more than 100 use cases. And then we can use that to fine-tune Llama 3.18b, which is a pretty weak model, which only gets 1% success rate on WebArena. But we can fine-tune it to reach the GPT-4 level, although it is not to reach GPT-4 level on WebArena and Web Voyager. But you know, it is not the best one. As compared to like the OpenAI's reinforcement learning learned computer use agent and other commercial closed source agent. And yeah, and the problem, and one problem I want to mention at last is that there are strong task interference between the websites. So you know, the data collected in like Web Voyager may not be directly useful for data used in WebArena. There could be a lot of problems. One is that our base model is too weak. It's just like 3.18b. If we use a larger model, it could. And second is that we are using a text-based model. If we change it to a VLM, the model could learn more transferable policy instead of the HTML, because HTML could look very different even for visually similar observations. Cool. The last one I don't have the time to go over is some social norms. Basically, when you are interacting with agents, you might expect them to follow certain kind of social norms. So, for example, imagine that you are hiking with your friends and they get stuck in the mud. What you should do, and for humans, there are like two kinds of questions that we might want to answer. First is a sensible action, which of the actions are acceptable, and the second is the best action among all of the possible acceptable actions. Which one is the best? And the question is that are like the norms learned in the large language model and the VLM, since they have consumed such large amount of the data. And the quick answer is they do not produce, even the best VLMs do not produce aligned answers with the human consensus. And we also propose ways to improve that through retrieval-based method, and we can find that it can achieve a much higher performance than the vanilla GPT-4o. And it's more aligned with the humans. Yeah, our data collection method is interesting because we asking the LM to perturb the context. It's more like LM is asking, what if you are not your friends are not hiking together, but you are competing in the race? What you should do? What if they are strangers? And then the LM could produce some of the answers, and we ask humans to label which ones are acceptable under this condition, and then in the end we can use the collected data to train the models. Yeah, and then it's very efficient. The only pipeline that involves the last human annotation is the last validation part. The prevents are completely automatic, which makes it very easier to gather the consensus annotations from prolific users. And yeah, some surprising result is that reasoning models are strong, even they are not given the visual input. There are visual reasoning models just came out like 2 days ago, but like we didn't haven't tested those. But from our initial result, if we just ask GPT-4 to generate descriptions, O3 Mini can give very good result as compared to other visual-based models like Gemini 1.5 Pro. And we also have open models which are doing very good. And they make different errors than humans. Humans have a lot of like norm prioritization errors. Basically, human among the acceptable ones, human make errors to choose choosing the best one. While models don't even know which ones are acceptable. And lastly, if you are using video VLMs, the way to input the video is very important. We have tried different ways, and we found that the best ways is actually not ones that are recommended by the official cookbooks. You do not input the video as a native input. You should concatenate the frames. It yields a much better result. And we also found that if you shuffle the order of a concatenated frames, you get much worse result. But if you shuffle the order in the native video input, you just shuffle the frame, so it doesn't make sense to you, but it still get like a reasonable result. Basically, the gap between shuffle the frames for the video input is much smaller than concatenation the frames. So it basically means that the native video input may not capture the temporal information that we get from concatenation frames. Yeah. And they can generalize to robotics. This is me interacting with a robot, and we use our method to do the embodied decision making, and it can generalize to unseen domains as well. Cool. This is just the summary of this, and then you can check all these ones. AutoLibra I will put on archive by the end of this week, but you can view the preprint over here, and the other two are public available. Cool. Happy to take it.
Yeah, thank you so much for the talk. Does anyone in here have questions? Okay, we have one question on Zoom, which it's from Adam Russell. He's not in the meeting anymore, but I was thinking of a similar question, so I'm going to use his wording because it's better. So he said the formula on slide 9 or 10 said something about optimizing social intelligence. What does it mean to, quote, optimize social intelligence? That's a real head scratcher for social scientists who long ago realized that humans are constantly satisficing and balancing multiple goals, reward functions, and that there really is no optimization available to social games of any realistic complexity, which is why we evolved social intelligence in the first place. So I think the term social intelligence is doing a lot of work here as a suitcase term and assumes that it's a thing that it isn't, or at least that it's much more than a single utility function. Defining social intelligence is the hard part here. Who is doing that work?
Yeah, that's so true. So that's actually the reason why we need to find the objectives that are not directly designed pre-hoc, but they should stem from the data, from the human feedback. So that's actually one of the reasons why we designed like AutoLibra. Yeah, and optimizing for that, I mean, humans it's true that the human may not be able to do the exact optimization in this like ours make term or like very rigorous mathematic formulation. But first, we are trying to find a possible solution. We are always trying to find a possible solution, just as you said. And second, you know, we also have our social goals that we want to optimize each day. So humans are doing some of the optimization. It's just like constrained by our you know, some of the social norm, our understanding of like the common ground with other people. So yeah, it's kind of ambiguous. It's not that rigorous as a mathematical optimization, but I think it's still optimization.
On that, I wonder, like, if you look at certain data sets which deal with ethics, I mean, ethics are trying to formalize what you should do and what you shouldn't do, right? You know, that may make it clear what the right answer is.
Yeah, and I guess one observation from ethics is that it's very culturally grounded, and so like, you know, it might be kind of a universal among humans that like stepping into the mud with your friend is not helpful and you shouldn't do that, but like I can imagine like a cultural differences in like how you prioritize among the sensible actions and like what the human would want. And so I'm curious, have you looked at all about like kind of, I guess, like cultural alignment in kind of machine social norms?
Yeah. So I myself haven't done research on that, but I feel like first it should be a data-driven approach, right? It is not like having some expert to annotate, oh, in this culture we should do that, and in that culture we should do that. It's mostly should be get things from ground up, right? Getting human preferences, when human interacting with the agents or in the like imaginative interaction, what they would expect the agents or robots to do. And then we can collect those and then convert that into some metrics in order to evaluate whether the agent's doing good. That's one aspect of the things, and the other aspect, I know a lot of work from like Gee's lab, who I collaborate most in Stanford, and they are doing like the culture kind of culture related norm collection. Yeah. I think that will come out very soon. Actually, yeah.
All right. Are there any other questions, either in the room or from the Zoom attendees? All right. Well, thank you so much, Hao. We're very excited to host you, and we still have a lunch spot open. So somebody please come to lunch.